Hi students, today we are going to discuss a very important topic which is called vertical circular motion. This is one kind of non-uniform circular motion. So you can look at the picture here. A body of mass m is tied to a string and it is revolved in a vertical circle. So let us assume this ball is tied to a string. Okay? And now I am going to revolve this in a vertical circle like this, vertical circle. So when the ball is revolved in a vertical circle, the tension in the string will be continuously changing, as well as the velocity, the magnitude as well as the direction of the velocity of this ball is continuously changing. From the lowest position, when it moves to the highest position, the magnitude of the velocity decreases. And again, when it is coming from the highest position towards the lowest position, the velocity will increase, as well as the tension in the string also will increase. So in this case, when the ball is going from the lowest to the highest position, what are all the factors which are decreasing the tension as well as the velocity of the ball decreases and reaches a minimum at the top. And then when it is descending down, its velocity increases as well as the tension in the string also increases. Okay? Hence it is an example for what? Non-uniform circular motion. Now when this object is revolving in a vertical circle and reaches the highest position, the tension in the string should be at least a minimum value below which the string will slack. So if the tension is not sufficiently minimum, then less than minimum means then the string will slack like this and the object will fall and it cannot continue the vertical circle. So when it is revolving at the highest position, this object should have certain minimum velocity with which it can complete the circle successfully. That minimum velocity required for the object at the highest point is called the critical velocity. So we are going to derive an expression for the critical velocity of this body revolving in a vertical circle at the highest position. And also the value of its velocity at two different positions we are going to derive. So since the velocity changes both in magnitude as well as direction, this circular motion is called non-uniform circular motion. Okay, you can look at the picture now. The different positions of the object is the starting point. Let us say A is the starting point or the reference point, and it is moving in a circular path of radius r. Okay, r is the radius, and B is one position followed by C and D. Now intermediate one position P also I have taken. P is some position. P is some position I have taken. When the body is reaching the position P, now the weight of the body, the weight of this object is always acting vertically downwards. And you can see that the string which is equal to the radius of the circle has moved from the position A to the position P. So the string subtends an angle theta with respect to the initial position. So when the body is moving along a circle, the string or the radius vector is sweeping an angle theta. So this angle is theta, and hence this weight mg is subtending an angle theta with respect to the extended position of the string. The string is extended by dotted line outward, so that this corresponding angle is also equal to theta. Now I am going to resolve this weight mg into two components. So this mg makes an angle theta with the direction of the radius vector. So what will be the component along the radius vector is mg cos theta, and the perpendicular component will be mg sin theta. Okay, so v is the velocity of the object at this point P. So look at the position P once again, children. The weight of the body is acting vertically downwards. It subtends an angle theta with the direction of the radius vector. So I resolve this into mg cos theta along the string and mg sin theta perpendicular to the string. Now the tension is another force acting on the string. So tension is acting on the string and it is acting inward. So tension is the inward force acting towards the center of the circle. And mg cos theta is the force acting away from the center. Okay. Now I will consider an arbitrary point P in between A and B. So I will consider at point P. Now T is the tension which is a force acting towards the center, and mg cos theta is a force acting away from the center, but still the body is rotating, means there is some centripetal force acting on the body. Therefore there is a net inward force. The net inward force must be equal to what? T minus mg cos theta. And this must be equal to the centripetal force FCP acting at the point P. So this must be equal to mv square by r, where v is the velocity of the body at point P, r is the radius of the circle, m is the mass of the body. Okay. So T minus mg cos theta is the net inward force acting towards the center, which is called as a centripetal force. So the same equation I can write in a different form like this. RT is equal to mv square by r plus mg cos theta. So this is the required equation 1. Now I am going to apply this equation for the lowest point A and the highest point C. Okay. So at the lowest point, so which is the lowest point here? This lowest point here is A. At this point, what is the value of theta is equal to 0 degree. At A, the value of theta is equal to 0 degree. Therefore, the tension in the string at A is denoted as TA. So the tension TA must be equal to, right hand side, m into VA square by R. Okay, plus mg into cos 0. Cos 0 is equal to how much? 1. So cos of 0 is equal to 1. So here if I substitute, then TA is equal to m into VA square by R plus mg. Okay. Now at the highest point, which is the highest point in this picture, it is C. So at the highest point C, what is the angle theta is equal to 180 degree and cos of 180 degree is equal to minus 1. So at this point, as theta increases from 0 to 90, then 90 to 180, then 270, then 360. So at this point, the highest point is C. The velocity is the minimum. So it is taken as VC. Okay. And the tension is taken as TC. So if I rewrite this equation 1 for the highest point, then it will be what? TC is equal to mVC square by R plus mg into cos 180. So mg into cos 180 is minus 1. So this is equal to mVC square by R minus mg. So this is another equation. So this is equation 2 and this is equation 3. Okay, I told you children, when the body is moving in a vertical circular path, not only the velocity changes, the tension in the string also is continuously changing. Is it not? First it moves from lowest to the highest point, the tension decreases. And again it increases when it moves from the highest to the lowest point. Okay, if the body has to continue the revolution in a circular path, there should be a certain minimum tension. Understand? So whether the body will continue the circle or not, it depends upon the tension in the string. Now there are three conditions. The tension in the string at the highest point, the tension in the string at the highest point is TC. So TC may be greater than 0. I will take the conditions. If Tc is greater than 0 means then the string will be taut. T-A-U-T, taut means it will be stretched, okay, it will be stretched tightly, and it is very safe for the body to complete the vertical circular motion. Definitely the body will complete the vertical circular motion when the tension is greater than 0. And if Tc is equal to 0, if the tension is equal to 0, now also the body will complete, okay, it will complete the circle, vertical circle, okay, with the minimum speed, with the minimum velocity, okay, and this velocity only is called as what? A critical velocity. The velocity will be minimum, just like the pass mark in every subject. Less than that is fail mark, is it not? Like that, less than this minimum velocity, less than this critical velocity, it will be not possible to complete the vertical circle. So the third condition is Tc less than 0. Less than 0 means does not, means the string will be slacking. So string will slack. Slack means you cannot complete, okay, so cannot complete the circle, cannot complete the circle. So under this condition, the condition Tc is equal to 0 implies that there is a certain minimum velocity with which the body has to complete the vertical circle. So we are going to derive an expression for the critical velocity. The minimum velocity at the highest point, this is the critical velocity. So the point is C, therefore its symbol is Vc, critical velocity. So for that, the highest point I will take C here. At the highest point, the tension Tc must be equal to what? 0. So Tc must be equal to 0. This is the required condition for the critical velocity. Now third equation is what? Tc. The left hand side must be equal to 0. Therefore right hand side must also be equal to 0. So m into Vc square by R minus mg must be equal to 0. So cancelling m, Vc square by R is equal to, right hand side if it goes means g, or Vc square is equal to g into R. Therefore Vc is equal to square root of g into R. So this is the expression for the critical velocity. Okay. So this is one part of the derivation only. Derive an expression for the minimum velocity required for the body to complete the vertical circular motion. See, for example, if you take the circus performers, in any circus means if you can see a globe, a cage. Inside that, motorist will be performing vertical circular motion. So for him, what is the minimum velocity required? He will calculate the radius of the cage into 9.8 meter per second square. Then we have to take the square root. So what value is coming now? At that speed only he has to ride minimum speed. Suppose if he is increasing his speed beyond this value, still it is safer and he will be pushed or pressed towards the cage in the outward direction. Understand? So like this, now if you want to find the value for the velocity at different points like B, P or any point like D, then we have to go by the law of conservation of energy. From the law of conservation of energy, we can find out the velocity at the lowest point. So I will find out the velocity at the lowest point for VA from the law of conservation of energy. So from the law of conservation of energy, the kinetic energy plus potential energy at every point must be the same, is it not? So I will compare the point A and C. I can compare the points A and C now. So with reference to A, the height of A is 0. Therefore the potential energy at A will be 0. Is it not? The potential energy will be 0. And kinetic energy will be equal to half m V square, is it not? So I will write conservation from the conservation of energy, kinetic energy at A plus potential energy at A must be equal to kinetic energy at B plus potential energy at B, or I will take any point. C also I can take. Okay, I want to get the velocity at A means I can compare with a known point like C. Now children, what is the kinetic energy at A? So this is equal to what? Half m into VA square plus potential energy at A is equal to what? 0. Understand? So this must be equal to kinetic energy at C. So this is half m v square C plus mg into height h. The height h of the point C with respect to A is equal to r plus r, that is diameter 2r. So this must be equal to what? 2r. Okay. Now up to this, have you understood? Now what I am going to do is I am going to erase this derivation so that we can continue this and derive the expression for the other velocities also. Okay. So now I will erase these points. Okay children, now you look at this. M is constant on all the two sides. So I will cancel this. And what are the remaining terms? Half. That is VA square by 2 equal to VC square by 2. So this is equal to VC square divided by 2 plus 2 GR. So this is a plus 2 GR. Now I want to take the LCM, is it not? So I can write like this: VA square by 2 equal to VC square by 2 plus 4GR by 2. So that LCM 2 can be cancelled. So VA square is equal to VC square plus 4GR. Okay. Now already we have derived VC square is equal to GR. Is it not? VC square is also equal to GR. So in place of VC square, what I can write? GR plus 4GR. Okay. Therefore, VA square is equal to 5GR. Therefore, VA is equal to what? Square root of 5GR. So this is again very important. This is the velocity, critical velocity at the lowest point. Lowest point, what will be the velocity? Will be equal to root of 5GR. Understand? So at the highest point it is square root of 1GR. At the lowest point it is square root of 5GR. Means what is happening when the body is descending downwards from the highest point to the lowest point, the velocity increases. Okay. Suppose in between one point B or D, let us take B for example. Okay. So at point B, so this is at point B, I want to find the velocity VB. Okay. So in between 1GR and root 5GR, it must be root of 3GR only. That we are going to confirm now. Okay. So for this, I will compare kinetic energy at B plus potential energy at B is equal to kinetic energy at C plus potential energy at C. Just like that in the previous case, unknown point on the left side, a known point C on the right side we kept. Like that, unknown point B on the left side, known point C I have kept on the right side. So B, at this point B, what is the kinetic energy? Half mv square plus potential energy. B is at what vertical height from A? It is equal to R. So this is mg into R, mgr. Okay. And this is now equal to what? Kinetic energy at C. We have already written here. Same I am going to write. Okay. Half mvc square. So this is equal to half mvc square plus mgh. H is equal to 2R. because the point C is located at a vertical height of r plus r equal to 2r. So now this m can be cancelled first of all. So the left hand side is what? VB square by 2 plus GR, okay, plus GR is equal to VC square by 2 plus here 2GR, okay, 2GR. Now taking LCM, I have to take LCM, is it not? So this one will be what? VB square by 2 plus 2GR by 2 equal to VC square by 2 plus 4GR by 2. So that now I can cancel the common LCM 2. So VB square on the left hand side, VB square is equal to VC square plus 4GR minus 2GR, okay. So this is minus 2GR. So this is now equal to VC square plus 4 minus 2 is what? 2GR, okay. Now once again, what is VC square is equal to GR. So I am going to substitute here. So this is now equal to, or this is equal to GR plus 2GR. So this is equal to 3GR. Therefore, what is VB equal to? So the velocity B is equal to square root of 3GR. So for solving numerical problems in competitive exams, surely you will get a problem from this topic. So you can easily remember, children, at the highest point the velocity is square root of 1GR, and at this point it is square root of 3GR, and here lowest point it is square root of 5GR. So it is increasing when it is descending down and decreasing when it is ascending in the upward direction. So once again I am repeating, my dear students, the vertical circular motion is a very good example for what? Non-uniform circular motion. Why? Because in this case both the magnitude as well as the direction of velocity changes. Suppose if you take the string attached to a ball, in this case the tension also changes, okay. And we have defined the critical velocity, which is the minimum velocity required for the body at the highest point to complete the vertical circular motion. Now during the Air Force Day, that is 8th of October every year, you can see the performance of the Indian Air Force pilots. So they will be flying in the aircraft and make vertical loop, that is called looping a loop, and they will be displaying the tricolors. So these are all some examples for the vertical circular motion. I hope you must have understood well. Fine.